Hi everyone, my name is Adina Badea. I'm the Director of Chemistry and Toxicology at Brown University Health, and I will be talking to you today about the basics of chromatography and mass spectrometry. So without further ado, what is chromatography? It is a separation technique. If you think back to your organic chemistry labs, you loaded your mixture of compounds onto the column, the pack of stationary phase, and you pushed it through the column using a mobile phase. As your mobile phase carried the mixture through the column due to the different interactions between the different compounds in your mixture and the stationary phase, the mixture separated into bands of individual compounds, and they eluted out separately at different times from the column. These bands, as they pass through a detector, form these peaks on what is called a chromatogram. If you think about it from a Gaussian distribution point of view, those bands are thicker in the middle or more intense in the middle than towards the edges, and that is why Gaussian distribution peaks show up on your chromatogram. The different compounds will then be characterized based on their retention time, that is the time it takes for them to come off the column. Now, depending on the nature of your mobile phase, you can have multiple types of chromatography. Gas chromatography, mobile phase is a gas, typically helium. Your sample, even though it starts off as a liquid in the liquid phase, is vaporized in a hot injector before it joins the gaseous mobile phase. Liquid chromatography, mobile phase is a liquid, typically a mixture of organic and aqueous solvents. Your liquid sample is injected into a stream of liquid mobile phases. Your column will be packed very tightly with stationary phase, so as the liquid enters the column, it will generate high pressure, which is why you see HPLC, high pressure liquid chromatography, or high performance liquid chromatography. Now, in terms of when to use one versus the other, you want to use liquid chromatography when the analyte is not volatile, or when it degrades if you try to vaporize it. Gas chromatography is best used for analytes that are volatile or don't degrade when vaporizing. Now, a chromatography instrument has four major components. Mobile phase, for a GC, it comes in a gas cylinder. For an LC system, it comes in a solvent container. An injector on both ends. A column, and I will highlight the differences between the different types of columns on the next slides. And then finally, a detector, which is where your data and all your data is coming from. So going one by one, for mobile phases, in a GC, your mobile phase will come from a gas cylinder. For an LC system, you'll often see these solvent bottles sitting on top of LC stacks. The inlet, for the GC, your syringe injects your sample into a heated liner where it vaporizes and then flows onto the column. Whereas for the LC, and I know this in more modern mass spectrometry LC-MS systems, the injector is hidden in the autosampler, but this is a picture from an older HPLC. Your tubing loop is loaded with sample while the mobile phase is diverted around that loop. And then you have to move the valve to the inject position, or it happens automatically in an autosampler, so that your mobile phase flows through the loop. This flow through the loop pushes the sample onto the column. Speaking of column, that is our next component. For the GC, your column is going to be fused silica open tubular capillary. This is a picture of a column inside a GC. The column is very thin. It is coiled many times. It is very long. If you were to uncoil the column, it could be as long as a football field. For HPLC, The column is a steel tube filled with particles of stationary phase. The columns are much more diverse. The LC columns are much more diverse. They can be thicker, they can be thinner, they can be longer, they can be shorter. And the material varies based on the criteria that you want to use to separate your components of your mixture. So pore size, hydrophilicity, hydrophobicity, chirality even. You have a lot more choices in a lot more diversity in choices in HPLC column. The nature of the stationary phase indicates the mechanism of separation. So in gas chromatography, the stationary phase is typically side chain functionalized polysiloxane. So the backbone of the polymer is this polysiloxane. And the side chains are what interact with the sample that goes through the column. The side chains tend to be methyl or phenyl groups. And so the analytes separate based on the degree of attraction to these side chains. So the more nonpolar compounds will be interacting more closely and eluting later. The analytes also separate based on boiling points, since we are talking about gas chromatography. So low boiling points will elute first, and then high boiling points will elute last. At the end of a GC run, the temperature of the oven is ramped up to elute all the high boiling points compound at the end of the run to make sure that your column is nice and clean for the next sample. In liquid chromatography, the stationary phase is typically silica with side chains. If you think back to your organic chemistry days, the silica in your columns, your hand columns, had side chains that were polar, and so the separation was primarily based on polar interactions. That is called normal phase chromatography, since that was the original chromatography technique. When the side chains are nonpolar, which is the case for a lot of the columns used in clinical labs currently, then they capitalize on nonpolar interactions, and this is called reverse phase chromatography. And finally, the detector. The goal of the detector is to create signal as the analyte leaves the column and flows through. Electrical signal is used to identify the analyte and quantitate its amount. For GC, common detectors are flame ionization detector, or FID, and electron impact quadrupole mass spectrometer, which is the typical mass spec in a GCMS instrument. For HPLC, a common detector is a simple absorbance detector, like a UV detector that continuously measures light absorbance at a specific wavelength. When we talk about LCMS setups, there are two major types of detectors, and ones that we use in my lab, triple quad, or QQQ, and quadruple time of flight, or QTOF. So without further ado, we're going to go through these one by one, the first one being the flame ionization detector, often coupled with the GC. So the analyte coming from your column is mixed with air and hydrogen and burned. This burning creates charged particles, or ions, that will flow between two electrodes, creating a circuit. The current flow through the circuit is measured by an electrometer. And this kind of detector is what we use to identify and measure toxic alcohols in blood samples. The next detector is an electron impact quadrupole mass spectrometer. In your source chamber, your sample is bombarded with electrons that break it into fragments of various mass to charge ratios, or M/Z. These ions are accelerated into the mass filter, which is the set of 4 rods, a quadrupole, 4 rods, which have voltage applied to them. This voltage will affect the path of any fragments that are traveling through. If the fragments are, the mass to charge ratios are compatible with the voltage of the rods, the fragments will pass through to the detector. These are also called resonant ions. If the ions are not compatible, they will hit the rods or the sides of the chamber. They will essentially go to waste. The detector is an electron multiplier, and we will talk more about it on the next slide, but every time a fragment hits it, an electrical signal is generated that the computer can count. By applying a series of voltages to the rods, you can obtain a mass spectrum, as with each voltage, a different mass per charge ion will go through to the detector. The detector is an electron multiplier. So what an electron multiplier does is whenever a charged fragment hits it, electrons are generated. Here, 2 per 1 fragment. These electrons will hit the opposite wall of the electron multiplier tube, and 2 more per electron. Electrons will be generated, and so on and so forth. And so as the electrons travel through the tube, the signal gets multiplied accordingly. The result is an electron impact mass spectrum. You have in this figure the mass spectrum for cocaine obtained on a GCMS. The mass spectrum is kind of like the fingerprint of a molecule. It contains the individual mass per charge fragments that resulted from the breakdown in the source of, in this case, cocaine. The intensity of each fragment denotes how stable the fragment is, the abundance of that fragment in the spectrum. The highest mass per charge is typically unstable, so you don't see it in a very high intensity. And then lower fragments tend to be a little more stable, and so you see them more prominent in a spectrum. Since the spectrum is kind of like a fingerprint for the molecule, you can use it to identify it if you are searching a library of spectra obtained by analyzing pure compounds. So in the GCMS, as your chromatogram goes, as the individual compounds flow into the mass spectrometer, into the detector, the mass spec is constantly creating spectra for every compound in these peaks. And so you have a mass spec associated with every LC peak. You can run the GCMS in 2 modes, full scan and simultaneous ion monitoring, or SIM. In full scan, every mass per charge ratio is scanned from 0 to about 500. This is a useful mode when you don't have a particular analyte in mind and you want to identify anything that elutes in your sample. This type of acquisition mode calls for untargeted analysis. So you can use this for a comprehensive drug screen, and I'm putting comprehensive in quotation marks because we are talking about a GCMS, and so you're not detecting any non-volatiles. So it's not truly comprehensive. In simultaneous ion monitoring, you will have a particular analyte in mind. So for instance, if you are thinking of doing a drugs of abuse confirmation on cocaine, like we saw on the previous slide, you only really need to look for a few preset mass per charge fragments. So if you think back to the spectrum of cocaine on the previous slide, we only monitor the fragments at mass per charge ratios 82, 182, and 303. And this calls for a targeted analysis. Now, why do we use simultaneous ion monitoring for confirmation? Well, if you only have a few mass per charge fragments to monitor, the filter can spend more time on each of these before the scan needs to repeat. And so the result is a higher sensitivity that can detect low concentrations of your analyte, which is what you want in a confirmation or a quantitative measurement. So why move beyond the GCMS? Well, as I hinted at beforehand, you do perform your analysis, your separation in the gas phase, and then you follow it up by a single phase mass detection. As a result, it's not appropriate for non-volatile or thermally labile polar compounds. You can make non-volatile compounds volatile through a sample prep, and we will talk a little bit more about that in a few slides. But it does tend to, GCMS analyses do tend to lead to a lengthier sample prep. So instead, the field has been moving towards replacing GCMS analyses with HPLC analyses connected to tandem mass spec. If you want a targeted analysis, typically you would use an LC triple quadrupole as your detector, and we will talk about that on the next slide. You can also collect data in an untargeted fashion, in which case you would want to use a detector that is compatible with that. In this presentation, we will talk about the quadrupole time of flight detector as an option, or the QTOF. In a triple quad detector, your ionization is going to be slightly different in an LC triple quad. You will have, most of the times in clinical analyses, electron spray ionization. So as your sample comes in liquid form from the column, it goes through the spray needle tip into the source chamber. And it gets sprayed, so droplets are generated in your source. Your source is connected to voltage. Your droplets are going to be, the molecules inside of your droplets are going to be charged. This charge is going to accumulate on the surface of the droplet because your source is also connected to heat. It's that at high temperature, your droplets are going to be evaporating. As they shrink in size, you hit the Rayleigh limit, which is the shortest distance two of the same charges can be next to each other before repelling each other. And so once you've hit that Rayleigh limit, you go into the Coulombic explosion, in which your droplet explodes into essentially individual ions, charged particles in gas phase. And so your ionized fragments will enter the mass spec in gas phase in the LCMS as well. And so the mass spectrometer is a triple quadrupole, which means it's a series of 3 of those 4 rod units that select for specific mass per charge fragments based on the voltage that they are connected to. So your first quadrupole will be selecting the parent mass, so the parent mass of the compound that you're trying to detect. Your second quadrupole is where your collision-induced dissociation occurs. So your molecules are bombarded with neutral atoms, and your molecules are broken into charged fragments. And your third quadrupole will select for specific fragments that you might be interested in. The result of that collision-induced dissociation is a spectrum made of fragments in a compound-specific pattern. Each fragment is coming from a specific parent ion and is called a transition. For increased specificity, we do multiple reaction monitoring. So every transition from 286, in this case, this is the spectrum of morphine, 286 to 268, for instance, or 229 or 201, these are all reactions. And so if we monitor multiple at a time, it's called multiple reaction monitoring. We typically monitor 2 transitions per analyte, a quantifier, and this is used to quantify the product ion's peak, and this is usually the most abundant in the spectrum. And then a qualifier, so this is an ion that is used to verify the identity of the compound, and we will talk more about how we use the qualifier in the analysis slides. The second type of detector that we're going to talk about for an LCMS today is one used for untargeted data collection, and that is the quadrupole time of flight. So similarly to a triple quad, you have two quadrupoles, and instead of a third quadrupole, you have a time of flight tube. Your first quadrupole can select the analyte of a specific mass per charge ratio or let analytes through. The Q2 can act as a collision cell, just like with the triple quadrupole, or in an initial stage, it can let all the analytes through. And then your time of flight tube will accelerate all of the ions that go in, offering them an elongated path, and also an opportunity to separate the masses based on the specific times of flight. A longer flight path means more resolution in mass of detection and identification. And because of this increased resolution in mass separation, these types of detectors are called high resolution mass spectrometers or accurate mass spectrometers. And this, to highlight this, I want to bring you back to the triple quads. The triple quads are typically considered to have unit mass resolution. So what that means is that if you have a mass that you have identified by a triple quad of a mass per charge ratio of 255, that means that you can be pretty confident that it's different from 254 or 256, but when you start going into decimals of mass, you lose that certainty. With a high resolution mass spectrometer, frequently you can go down to 3 decimals or more of mass units. And so within that higher umbrella of 255, you would be able to differentiate lamotrigine, which is an anti-epileptic drug, which has a mass of 255.007, from 2CT4, which is a designer amine, which has a mass of 255.129, from diphenhydramine, your Benadryl, which has a mass of 255.162. And I know that I'm sorry for putting math on your screen here, but this is just to show you that when you relate the kinetic energy of the individual particles entering the time of flight tube and the voltage applied to the TOF, you can get a relationship that essentially shows you that by very accurately measuring the time of flight, you very accurately measure mass per charge. So that is how you get your very accurate, very high resolution mass per charge measurements by measuring that time of flight. As I said before, this is very much amenable to untargeted data collection, and you can use the time of flight to separate all the parent ions and all the fragments that are separated. Now you could collect data with a QTOF in a few modes. The first mode is information-dependent acquisition, and this is what we use in my lab. All of your ions are going to be separated or detected in the TOF tube. If a certain ion exceeds an intensity threshold, then it will trigger the Q2 collision to generate fragments, and then your fragments will be separated in a TOF tube, and you can collect enhanced product ion spectra based on that. A second mode of acquisition is SWAT, sequential windows of acquisition of theoretical fragments, during which you let all protonated analytes within a 25 Dalton mass window through Q1, fragment them all in Q2 simultaneously, record them in the TOF, and then you repeat for the next Q1 window until you've reached the final mass and it's all stitched together by the software. There's also MSE or MS everything, where you alternate between low collision energy, where very little fragmentation happens, and high collision energy, where all the ions are fragmented and they all coalute and go through the quad and cell and separate into the TOF. As you might imagine, this is a very complicated data set, regardless of which mode you use. It's a complicated data set that requires specialized software to identify the samples. So why use a QTOF at all? Well, so for us, it plays an important role in emergency and critical care situations. In these settings, drug screening results will not influence management if they take too long to perform, they're not specific enough, or not sensitive enough. Currently, a lot of EDs just use immunoassays because they're fast, but they have very limited specificity and sensitivity. You could use GCMS or another kind of targeted mass spec, but it is very time intensive. A lot of these methods are batched. With LC-QTOF, you can achieve the specificity and sensitivity of a mass spec system and get closer to the time efficiency needed to influence management in a complicated ER case. So a lot of our QTOF methods are, especially for urine, dilute and shoot, so they're very fast. We'll talk about sample preparation in a second. And so you could use a QTOF to perform a real-time comprehensive drug screen. Now, of course, the drawback is that typically QTOF systems can cost a lot of money, so not all medical centers will have access to this necessarily. I talked about sample prep, and so I just wanted to bring you all back to what an LC-MS analysis workflow looks like. So the first step is to get your sample from its original container in a form that is compatible with your instrument. So your sample prep will differ based on the kind of sample that you have. I have pictured here urine, blood, and oral fluid. You then have liquid chromatography that separates your analytes, and then mass spectrometry for each of the separated analytes. So what is the role of sample prep? Sample prep plays a big role because depending on your sample collection and the particular samples, you may have preservatives or matrix components that you might want to remove before they hit your instrument. Sample prep increases sensitivity by removing these interfering components, and it also gets your sample into an LC compatible solvent. It also has an important role in extending the lifetime of your LC consumables, and so you can use that to adapt to whatever LC limitations you might have in your lab. So what are the kinds of sample preps that you may see out there? So you have dilute and shoot, and so this is for simple matrices. It's fast, it's cheap, it's easy. Protein crash and precipitation for dirtier matrices, it's still fast and still cheap and easy. You can follow this protein crash by dry down, which makes it a little less fast, or dilute and shoot post-centrifugation. Liquid-liquid extraction, this leads to better matrix depletion. Solid phase extraction, even better matrix depletion. You can use supported liquid extraction and extraction sample prep or plates for 96 well formats. Now, what are matrix independent factors that you should be considering? Sensitivity, this is going to be analyte specific and depend on whether you have old instrumentation. Mobile phase restrictions, column restrictions, instrument time. Do you need to have a shorter run? In which case you may need your separation, your sample preparation to be more extensive. And then cost. What cost per sample prep supplies versus cost per sample or reagents are you willing to take? Upfront investment in automated liquid handler, are you able to do that? And what amount of sample are you willing to sacrifice for each analysis? Other factors, time, and that is turnaround time. Are you going to batch your samples? Are you going to have online or open access analysis? Time for development, more complex sample preps require more development. Time for instrument maintenance. The more intricate your sample prep, the longer you're going to have between having to perform maintenance on your instruments. Time between service and PMs in the same line with instrument maintenance. This is more involved instrument maintenance. And then finally, staff. What type of experience with LC-MS/MS workflows do your staff has? Do you have time dedicated to LC-MS method per day? And generally, how much time do you want to dedicate to sample prep? And I want to illustrate some of these factors by looking at dilute and shoot. Is it really as dreamy of a sample prep as it sounds? It's typically used for urine broad screening panels. It's fewer steps, which means fewer instances for human error. It is cheap, although you have to mind the hidden costs of more frequent LC consumable replacements. It is fast, and so if you're targeting the ED and ICU patients with the service, definitely one to keep in mind. It's easy on staff, or is it? Because it does lead to more involved weekly and daily maintenance sheets. Definitely faster in development, and it does allow you to not batch, so that allows for some flexibility in scheduling. However, there are pitfalls. High background can hide the signal. Can you see the octopus in this picture? There is one, and if it's hard for you to see, that's how hard your signal is to see for your instrument when you don't clean up your sample. You can have ion suppression, source suppression, co-eluting compounds. They compete for charge in the source. You're going to have more frequent instrument cleanups by staff and more frequent PMs. Protein crash, also simple. This is for more protein-heavy matrices like serum, plasma, oral fluid. It removes a decent part of the interferences that cause clogging and aging of LC components. It is cheap, it is easy. It can be fast if coupled with dilute and shoot post-centrifugation. It can be sensitive. If you want, you can dry down and concentrate upon reconstitution. Having gone through all of that, what are the types of analysis that one can do with chromatography? So you can have targeted analysis where you know what you're looking for. So this is for therapeutic drug monitoring or for confirmations for drugs of abuse or for alcohols in blood. Or you could have an untargeted analysis where you're not looking for any one specific analyte. And these are your comprehensive drug screens, where you detect all drugs that are present, not just those detected by immunoassays, and examples of analytes that might be covered in these analyses that you would miss with immunoassays: poison mushrooms, synthetic cannabinoids, or rare prescription drugs, or even recreational drugs. So to bring it all together, I'm going to walk you through a targeted analysis, which generally has 7 steps. The first one is to prep your tubes with standards of varying concentrations, your patients, and then you add an internal standard, and I'll tell you what that is in a second. Step 2, hydrolyze off the glucuronide. At least for us, that is necessary, a necessary part of sample prep, and I'll talk you through what that is as well. Step 3, extract your analyte into organic phase. Step 4, evaporate the organic phase. Step 5, if it's HPLC, you just resuspend in mobile phase. If it's GCMS, you might need to derivatize. Step 6, inject. And step 7, perform your targeted analysis. Step 1, what is an internal standard? So it is a chemical that is not found in the body or sample, but can be added to the sample for analysis. It needs to behave chemically identically or as close to the analyte of interest as possible during the sample processing and chromatography. It is added to make sure that nothing went wrong during your sample processing or during analysis. It can also make your quantitation procedure insensitive to injection errors. So for instance, if you have no internal standard and you have a small analyte peak, you don't really know if it's small because there is little analyte in your sample, or because there might have been a bubble or some other type of injection error. If you add internal standard to a sample and you have a small analyte peak, if your internal standard is much bigger than the analyte peak, then your injection was likely fine. However, if the internal standard peak is also small, that is a sign that your injection was bad. Furthermore, if your signal is the ratio of the height of your analyte over the height of your internal standard, then that ratio is, to a certain extent, insensitive to port injections, which will also eliminate, in many cases, the necessity of repeating your analysis. And more on that on the quantitation slides. Step 2, hydrolyzing off the glucuronide. So the body conjugates glucuronides onto drugs to make them more polar and to speed up their excretion into urine. There are two types of glucuronides, those with an ether linkage and those with an ester linkage. We, especially in our lab, we need to unconjugate the analyte to make it nonpolar so that we can analyze it by reverse phase HPLC. And we remove this glucuronic acid by a hydrolysis step. You can hydrolyze the linkage either with hydroxide, especially for ester linkages, or with beta-glucuronidase for ether linkages. In this image here, I am showing you how we react with glucuronidase on a hot block. There are glucuronidases out there that work at room temperature as well. Step 3, extraction. What is extraction? Well, you're moving your analyte and internal standard from your aqueous solution, that is your sample, into organic phase. Why would you want to do that? Well, in that process, you're also leaving your interfering substances behind. And there are two ways to do that. One is liquid-liquid extraction. So if you have an acidic analyte, you add acid to make it neutral. If it's basic, you add base to make it neutral, and then you can extract into a nonpolar solvent like N-butyl chloride. The second type of extraction is solid phase extraction. So if you have a basic drug, you can add acid to make it positively charged, and then you pour it onto a solid phase extraction column filled with resin that is negatively charged. You wash the interfering compounds while the analyte stays bound to your SPE, and then you elute with a solvent that has high pH, turning your compound back into a neutral form so that it comes off the SPE. This process is called bind and elute. And here I am showing you pictures of how this bind and elute process can work. Here we have bigger SPE columns. These we use for samples that are processed individually. And here you have a sample extractor, a pneumatic extractor with in-tip SPE. I know it's a little hard to see, but every well of these 96 well plates have a tip that goes into each well, and that tip has resin in there that is SPE. Step 4, evaporate off the extraction solvent. And there are a couple of reasons why you might want to do that. One, you need to perform a solvent change. After the extraction, you typically have your analyte in an organic solvent. You probably want to move it into a different solvent if you have to derivatize, or if you want to get it into a mobile phase for your HPLC. A second reason is you might want to concentrate. So if you want to increase your lower limit of detection, you will evaporate it off and then resuspend in a smaller volume of liquid before you inject it onto your chromatography machine. And here is an example of how you might do that. These are hot blocks, and the evaporation happens under a stream of air. Step 5, if you're using an HPLC, then you resuspend in mobile phase and you're ready to go. If you're using a GC and your analyte is volatile and thermally stable, you resuspend it in a volatile solvent and you're ready to inject. This happens especially in those comprehensive drug screens by GCMS. If your analyte can be made volatile, you will have to derivatize, and we'll talk about that on the next slide. The derivatization is the addition of a nonpolar functional group to your analyte that makes it more volatile so that you actually can see it by GC. Derivatization and has specific reagents. You can silylate your compound with BSTFA or acylate your compound with trifluoric acetic acid. And so any compounds that has these YH groups, and for each derivatization agent you have slightly different YH groups, can be turned into a volatile derivatized compound by the addition of TMS or TFA. Once you have your compounds, you are ready to inject. And again, if you have a GC, you inject in a heated liner that vaporizes your sample. If you have an LC, you are injecting into a loop that then joins your sample with a liquid mobile phase. Step 7 is analysis. If you have LC without mass spec, so if you have HPLC UV or a GCFID, you are going to identify the compound based on relative retention time. So your relative retention time is the retention time of your analyte divided by the retention time of your IS. You calculate that for your unknown peak in your patient sample and then compare that with the relative retention times of the peaks in your standard injections. And that is how we identify the analyte. Your chromatogram will look something like this. One of those is your internal standard and two of those are analytes. If you want to quantitate without mass spec, you will still first make a standard curve, inject a set of standards, each at a known concentration to make the standard curve, and a plot of concentration versus your height ratio between the analyte and the IS. You then find a slope, which is called the factor, and then we measure the ratio for the patient, and then you use the standard curve equation to calculate the concentration of the analyte using this reaction. So your concentration is going to be the factor multiplied by its individual ratio. If you have GCMS and you're running simultaneous ion monitoring mode for the most abundant ions for the analyte and IS, to quantitate, you want to extract the ion chromatograms from the data. One is for the ion unique to the analyte, the other one is for the ion unique to the IS. This is just an example for a standard THC metabolite. I know they're old pictures. We haven't done GCMS for this in a while, but I still teach it. And so you want to quantitate similarly as for HPLC UV. So just to give you an example, if you have a standard of 33 nanograms per mil and the analyte height is 33, the IS height is 1, then your factor will be 33 nanograms per mil over that ratio height, which will give you 1 nanogram per mil factor. And then in your patient sample, your analyte has the height of 100 and the IS has the height of 50, then your concentration will be the factor multiplied by the ratio. So that is 2 nanograms per mil. For analysis in LCMS using a triple quadrupole, you identify the analyte by comparing the area ratio to the standard and by comparing the retention time of the patient to the standard. Additionally, because for each analyte we monitor 2 product ions, remember the qualifier and the quantifier, we also use the ratio of the area of the qualifier over the area of the quantifier. This should be constant for any analyte because remember what you're doing is you're measuring the intensity ratios of those 2 product ions within the spectrum of your molecule, which should be unique to your analyte. And so you compare this ratio in the patient sample to that in the standard. If the ratio is the same, then you have identified the compound as what you think it is. And so for instance, in this example, on the right, I have my morphine standard. The qualifier to quantifier ratio is 1 at the retention time of 1. And in my patient, I have a peak at the retention time of 1. However, even though I can see the quantifier and qualifier mass per charge fragments, their ratio is not the same as the one in my standard, and so this is not morphine. This is just an interferon that looks similar to morphine. I also wanted really quickly to walk you through a QTOF analysis, and so for this analysis, the software will look at 4 specific factors and display the most probable identification. So the software looks at mass, retention time, isotope, and library match. The score, the overall score, needs to be 70 or more in order for the result to even display. And so just going one by one for this peak that is tentatively identified as quetiapine by the software. So the mass is accurate. The retention time matches that in the system. And this is the kind of system where you build your own libraries by ordering pure standards and recording the retention time and the spectra as you build a method. The overall combined score is very good as well, 98. The spectral match on the top, it's in blue is the spectrum recorded in the sample, and at the bottom is the spectrum from the library that was recorded when a pure standard was analyzed. And as you can see, it's a match. And then finally, there's the isotope ratio. So the software looks at the formula of the specific compound that you are trying to identify it with or to match it with. And based on the number of carbons, it generates, or other atoms with isotopes, it generates the expected ratio of mass plus 1, mass plus 2, and pulls that from your sample and matches it. So the gray and the gray is what is expected and the blue is what is in your sample. And as you can see, it's a perfect match as well. So it's a match. And with that, we are at the end. Thank you so much for sticking it out through the entire presentation. I have a couple of summary slides. I'm not going to read through all of them, but I wanted to make sure that you get an overview of all the topics that we talked about. And this is my final summary slide, and as I give you a couple of seconds to read through it, I just want to say thank you so much for your attention. I hope you got a lot out of it, and I am looking forward to answering your questions in the live Q&A. Thank you again.